This is FRM Part 1, Book 2, Quantitative Analysis, Chapter 16, Simulation Methods. Let's look right at the learning objectives. We're going to do lots of describing and lots of explaining. Basic steps of Monte Carlo, describe sampling error, explain how to use antithetic and control variates. We'll look at the benefits of reusing sets of random number draws. We'll talk about bootstrapping. We'll describe pseudo-random number generating. And then we'll talk about some disadvantages. So let's go ahead and get started with Monte Carlo simulation. I mean, this is really kind of a cool thing because what it does is it accesses computer power to try to make predictions of what's going to happen sometime in the future. And so notice the definition that I have there. It involves creating a model into which all of the variabilities and correlations of the input criteria are entered. So we spent lots of good time talking about variances and covariances over the last couple of chapters. What we're going to do is we're going to use those as inputs, and then we're going to simulate the process over a large number of outcomes to obtain a spread of results. Now, what happens in order to work through this Monte Carlo simulation, you have to utilize a sequence of random numbers. And so I want you to think about this example here. Let's suppose that you're a financial advisor and you have a client who's 50 or 60 years old, and that client comes to you and says, when I die, and by the way, I expect to die when I'm 80 or 85, I would like to have $1 million. And that client currently has a certain number of dollars to invest. Maybe it's a couple $100,000. And the client also says, I want to withdraw $20 or $40 or $80,000 every year. And you get together and you visit with this client and you say something like, I think a 5% money market, a 25% fixed income bond fund, and a 70% managed equity fund. I think that'll get you to your goal of $1 million by the time you're 80. And so think about, you got this, you have all these assets inside of the asset classes, and so you can compute the variances and all the covariances. And what you want to do is you want to generate some random numbers and assign those random numbers to potential outcomes so that, think about the best case scenario. If everything goes really, really well, then the client might have $2 million at the time of death. If things go really, really poorly, maybe the client will have $0. But of course, we're interested not in the extremes, but we're interested in everything that goes in between those extremes. And what this Monte Carlo simulation will allow us to do is run hundreds, maybe thousands, maybe even tens of thousands of these sequences, and it's probably going to follow something close to a normal distribution. All right, so look at the little model I have below at the bottom of the slide. We have those decision variables. We're going to input those into the simulation model. That model, and we'll talk about random number generation here in just a little bit, and that's going to put together some output, whether it's a terminal value of a client's portfolio, or the future value of a bond, or maybe we can reverse it and compute the present value of a callable bond. But we can do all this Monte Carlo simulation to help us manage risk. Here's a good graphic example of something that kind of looks like a normal distribution. If you turn your head sideways, don't get vertigo if you do that. Here we go. We have a stock that's currently trading at about $35 a share. And we come up with some inputs, whatever those things are. And you can do this in Excel actually relatively easily for something like this. And you see all the different colors. Those are all the different paths. And so notice what happens there. Best case scenario, the stock price looks like it might be, $57? And down at the bottom, it's hard to tell, $20 or whatever. So there are probably some that even go a little bit below that didn't show up in the picture. Here's some other good examples. Pricing of exotic options, because there are numerous random paths. Each of those paths that the underlying asset, which could be a stock, it could be an index, it could be could be a commodity, could be anything. And each of those paths is going to have an associated payoff. And so you discount those back and take the average to get the option price. You can also do this with macroeconomic variables like inflation or interest rates changes or GDP changes to try to estimate what's going to happen with Fed decisions or what's going to happen to the macro economy or oil prices. And then this is probably most important for financial risk managers conducting stress tests. I mean, financial institutions, they do this all the time, and they run these Monte Carlo simulations. Sometimes it takes all night long to run these because they're doing this over and over again. There's so many there's so many different variables. I mean, think about the balance sheet for a financial institution. On the left-hand side, you have all the assets, right? And on the right-hand side, you have all the liabilities. And so those liabilities, the deposits, those liabilities, those are accounts that the financial institution owes today, right? So if somebody shows up, they have to come up with that cash. Well, then, of course, there are longer-term liabilities like maybe a certificate of deposit or something similar to that. But then you get into notes and bonds and all different other sorts of fixed income securities. And for a financial institution, that makes up the bulk of the right-hand side of the balance sheet. And then there's just this little slice of equity. And so these capital requirements, this has been a huge issue, especially in the United States, going back to the 2008 crisis and even way before that. So these Monte Carlo simulations allow for stress testing. What happens if oil prices go up? What happens if inflation goes up? What's going to happen to the threat of bankruptcy or the threat of insolvency for this financial institution? All right, so here are a couple of steps here. These are simple. How can Monte Carlo simulation be conducted? So we generate data with respect to a desired data generating process. And of course, we're going to have some errors. We can run some regressions, calculate a test statistic. We can save that test statistic, and then we can go back and do it over and over and over and over again. Notice at the bottom, I say that n should be large. Clearly, thousands of these things are going to be run. Now, the issue here, let me go back to this picture here. The issue here with Monte Carlo simulation is the resultant volatility or variance or standard deviation of all of these possible outcomes. So remember when we talked about simple linear regression, we did that method of the ordinary least squares. And what we were trying to do was minimize the distance between the line and each one of those observations and predictions, whether we were above the line or below the line. Well, Monte Carlo, it's a similar kind of a process as the ordinary least squares, but what we want to do is try to minimize. So let me go back here. What we want to try to do is minimize that sampling error. I call it reducing the sampling error in this slide. And so the first way is generally an easier way to increase the sample size. But of course, if you go from 1,000 to 10,000 of these simulations, there's a cost to it, the human cost of programming and then the actual computing cost of staying up all night long waiting for the outputs. So method one is going to be like a marginal cost, marginal benefit decision, but there are some other variance reduction techniques that are fairly interesting. So let's start with this antithetic variate technique. All right, what we're going to do is we're going to take a complement set of random numbers and running a parallel simulation. You guys know that I like to give sports analogies and even movie analogies. So I go back to one of my favorite movies that I watched with my children over the years, Back to the Future. Do you remember in Back to the Future Part 2? There was the regular old 1985 and then the alternate 1985 that Doc and Marty had to deal with. So I think about these Monte Carlo simulations as alternate 1985s. Of course, Marty and Doc only had to deal with two of those outcomes, but with a Monte Carlo simulation, we got tons and tons of these paths, right? And so what is the goal? The goal is to try to come up with all these paths that has the lowest possible sampling error. And one way to do that is to generate a set of random numbers and then maybe take the inverse of those random numbers, and I'll talk about that in just another slide, and run a parallel simulation. So you've got the regular kind of a simulation, and then you have a parallel simulation. And what's going to be really, really cool is that there's going to be some interesting applications to the correlation between those two. I'll mention that in another slide or two. So we simultaneously simulate a parallel path using those already generated numbers. Now, here's the cool thing about this is that because you are using these complement set of numbers, the correlation coefficient between those two is going to be negative. And we know from our conversations back in portfolio diversification that if the correlation coefficient is 0 or negative, then the volatility or the standard deviation of the portfolio falls. So that same application of the importance of covariance or correlation holds true here. Let's do just a little bit of math, and then in that bottom blue box I'll tell you a little bit more about that negative covariance. So here's an example, two variables, x1 and x2. What we want to do is we want to find the variance of the average of these two. And this is what we use in lots of times in pricing of financial securities like a call option. We have to take the average of two possible bond prices inside of that callable bond, and we take the average. So there we have the divided by 2, but the variance of this is going to be 1/4, and then notice that far right term is 2 times that covariance. Now, because of this parallelity, is that a word? I'm not sure that's a word. Because of this parallel simulation that we're running, that covariance is going to be negative. So look at the bottom blue box I have there. So we're going to draw some random variables from a uniform distribution, right? 0 to 1. We're also going to include this parallel thing, this parallel back to the future universe of 1 minus u. And the universe of the u compared with the universe of 1 minus u, that's going to have a negative correlation coefficient. And so that's going to reduce this sampling error. Now, the second way to do this is through a control variate technique, which is similar, but it's a little bit different in that we're going to use some properties known prior to the simulation. Now, we know that the effects of the sampling error for this problem under study, like pricing an option or pricing a callable bond or pricing terminal value of a portfolio, but those known problems will be similar. But these effects can be reduced by calibrating the Monte Carlo results using the analytic ones. Let me give you an example here. Let's suppose that we want to value option A, but we already have an accurate valuation for a similar option B. All right, so what we're going to do is we're going to use the same numerical procedure to value both A and B, even though we already know the value of B. All right, if the estimation errors are unbiased and highly correlated, then that technique enables us to produce a better estimate of the value of A. All right, so look at what I have here in the bottom. So the accurate value of option B, that's P sub capital B, and then our estimated values of option A and option B. So with this control variate technique, we're going to estimate the P hat star of A given by, well, the difference between those two estimates added to the known value of B. So what we're doing is we're controlling. That's why we call it the control variate. We're controlling it by using stuff that we already know. We already know what that accurate valuation for B is, and then we're just going to make an adjustment. So think of that plus sign to the right of the P sub B as an adjustment due to our estimates of both A and B, right? We already know B. We're trying to estimate A, so those two estimates, we're going to use the difference between those two to come up with our estimate for A. Now let me jump right into the example here, and then I'll go back and explain this reusage. So let's suppose that we're trying to price options on an individual security or an individual index, and the only difference is the time to expiration. So we might have a 1 month option, we might have a 3 month option, and a 6 month and a 12 month option. All right, so what we can do then is we can use the data for the 1 month option to help us price the 3 month option, or vice versa. So that's what we're doing here. We can reuse some of these random numbers across experiments so that the variability in the difference of the estimates across those experiments can decline. That should make good sense. Bootstrapping. This is a fun concept back in my PhD days. This is what we used to do. We used to look at the spot yield curve for, let's say, Treasury securities. And what do we know? I mean, we can go out and we can observe, maybe the 1 month and the 3 month and the 6 month and the 12 month. We can observe those spot rates, but we don't know what the 100th day or the 311th day. We don't know what those spot interest rates are along that yield curve. I mean, we can put it in Excel and we can force it to be a curve, but it's really just going to be a bunch of lines in between those spots. So what we try to do is we bootstrap so we can get those individual ones in between the known values. And that's what we're doing with bootstrapping here. Notice in that second block point, bootstrapping takes the data as given and just resamples it over and over again. Think of it as a type of non-parametric Monte Carlo analysis. Now, I never did thousands of simulations when I did the bootstrapping back for those spot yield curves, because you can come up with some pretty reasonable estimates with just some pretty simple mathematics. But if we're trying to do this over an extended time period, the bootstrapping can involve thousands of simulations. Now, the cool thing about bootstrapping is that there's no assumption made about the underlying distribution or its properties are assumed. So look at this here. I got some interest rates down the left-hand side, and we're limited in the number of observations. So what I'm going to do is just make copies of those things, maybe 1,000 as I have in the middle block there, maybe thousands of these. And then we're going to create a much larger sample to work with, and then we're going to pick random samples out of that much larger sample. Now, of course, bootstrapping is very effective for spot yield curves, but it's not terribly effective if there are lots of outliers or if there's a problem with the independence of the data. Most computer packages include a random number generator. You can do this very simply in Excel. They're generated from that uniform distribution, which means that within that interval, every value has an equal chance of being generated. A discrete uniform number generator would be a roulette wheel, and I have had almost zero success playing roulette over my lifetime. How about a pseudo-random number generator? This is an algorithm that uses some mathematical formulas to produce sequences of random numbers. And so what happens here is that these sequences then approximate the properties of random numbers. So it's possible to generate numbers that meet all of the statistical properties of random numbers by carefully choosing those values of the parameters. Now, here's an example. Let's suppose that we've got this regression equation where y is equal to ay. Now remember, here we got I plus 1 and then I, so it's the next step, right? The next draw, so to speak, plus some increment. We'll note that as c. And then what we're going to do is we're going to divide that y I plus 1 by m to get the remainder. All right, so there are t random draws that initial value is y sub 0, and that's called the seed, and then the multiplier is is the A, and the increment is noted as C. So what we're doing here is we're going to really just, I mean, think about this, start at some number, 0 or 10 or 100, whatever it is, and then you're just going to try to go up incrementally, whatever that is. And it depends on the remainder. So that modulo, remember that's the remainder of dividing two numbers. Now, those first few generated variables are always going to be heavily affected by the choice of the seed data. Now, why is a good simulation design allowing for this phenomenon? By generating more data than are required and then just dropping those first few, right? So if you got 12,000 of them and you can eliminate or reduce the effect of that choice of seed by just ignoring the first 1,000 or 2,000 or however many you think. Here's some disadvantages of simulation. Calculations can be long and sophisticated. This is what I was saying earlier about the overnight. Replicating the results can be difficult. That one screen I had earlier, that one slide with the stock that was trading about $35 a share and had all those colors going out, sometimes it's difficult. Now, in a case like simple stock price, that's probably going to be relatively easy to replicate. But go back to my example with the client who's 50 or 60 years old, and you get this giant range of terminal values, that might be difficult. You might not get precise results. And if you don't put anything good in there, you're probably not going to get anything good out. I remember hearing garbage in, garbage out. That was even when I was in college in the early 80s. Now, remember what we talked about in just our previous chapter. We talked about correlations and how correlations rise during periods of financial stress. Right when we need the diversification benefits, they tend to fail us. Well, Monte Carlo simulation suffers from a similar disadvantage. It tends to underestimate the probability of extreme events. Notice what I have in the bottom right there. Not only did correlations fail us, but Monte Carlo models failed us 10 years ago or so as well. Now, so this is just a disadvantage. I mean, of course, there are lots of advantages that we talked about during this slide deck. So Monte Carlo has lots and lots of really good things to help us manage risk, but once again, it's not perfect. So sooner or later, we're going to have to figure out how to handle those tails. And that takes us through book 2. I'll be looking forward to seeing you in book 3.